Okay, so I'm Robin. I work as a software consultant for TNG in Munich. And I want to talk about HyperLog. Who knows HyperLog? That's nice. I hope at the end everybody knows it. So HyperLog is a data structure. It's a very basic thing, but it's not well known. I think it's really useful to know absurd data structures. So what problem does this solve? The problem is counting unique elements. So you have a collection of things, like this bag on the right, and there's some blue objects, maybe duplicates, some other objects, and you want to count how many unique objects are in there. So what does the Python programmer do? Okay, you take a set, put it in there, and do the size of the set, and that's it. Okay, easy solution. The problem is this doesn't scale well, because you need memory for it. You need to actually store a copy of each of the unique elements. So if you think about millions of objects, you have maybe some data stream going by. Typical example is like unique visitors of a web page. You don't want to store all their IPs. Maybe you are not allowed to. So what do? You want some kind of streaming mode, and you want some algorithm that deals with millions and billions of elements. So what's the idea of the algorithm? The idea is it's a probabilistic data structure. So it's not an exact result, but it's an approximate result. You use less storage, so order 1 or some other small scaling. And how does it actually work? So let's go through it. You take your object, you hash it. So you have, for example, a 64-bit representation of your object. And for each of those hashes, you count the number of leading zeros. Very simple operation to do. And then your estimate is just you look at what is the longest sequence of zeros you ever saw while going through the dataset, and 2 to this number is your estimate. So for example, here you have a couple of hashes. You have maybe 2 leading zeros, 1 leading zero, or 3 leading zeros. And if you see this, you take the maximum of all the numbers you see. It's 3 in this case. So your estimate is you have 8 unique elements in the set going through. Okay, so this is a pretty rough estimate. The only thing you can do is like powers of 2. But it's already very nice. It stores only one number. You only have this maximum that you have to store. And it's very CPU efficient. But you still have to work on the accuracy. So how do we improve the accuracy of this algorithm? The idea is we extended the storage a bit. So what we do is we start with the hash again. And then we split the hash in 2 parts. The first part is to choose a bucket. And the second part is then treated as before. So in this example again, we have a hash of 8 digits, 8 bits. And we take the first 4 to choose a bucket. So there's a bucket named 0011, there's a bucket 0101, and so on. And then for the second part, we do the previous algorithm of counting the zeros. So we have values in this buckets of 1, 1, and 2. And for each bucket, we only store the maximum length of the zero sequence again. So our storage is m buckets. And we can tune this number. For the CPU, it's still very, very little effort. There's some bit operations to get the bucket and truncate stuff. But we now get this chance to increase our accuracy because we not only have one number, but we have m numbers. And in statistics, everything scales as 1 over square root m, and also in this case. So we can tune this. And the nice thing about this algorithm is still with this multiple buckets, it works nicely with streaming data. It also is trivially to parallelize. So you just split up your stream on multiple machines or cores, and each of them calculate the buckets separately, and then you merge the buckets by calculating the maximum over all buckets. So how does this work in practice? This is also the way I learned about this algorithm by using Redis. In some Redis workshop, we looked into this. So Redis has an implementation of HyperLog. It uses a fixed memory size of 12K. And reading about their memory storage is also very funny because they have 6-bit elements they store, and argue why this is more efficient than using full bytes. And this fixed memory allows them to count stuff with less than 1% error, up to 2 to the 50 objects, which should be enough for everybody. This is the usage example. So you just put the bucket, so you have some storage object called languages. You put objects in there, it counts them, you can get a count, and you can merge multiple of those counters together. And some links for further reading. So the first one is about the implementation in Redis, and the second is the original paper. And as a general suggestion is look at those data structures. This is a very absurd one, but there are many really useful ones, and it's nice to know them. Thank you.